Hello everyone and welcome to our channel, MooTechie. A special welcome to all the dairy technologists and students tuning in. Today we are excited to begin a brand new unit. This is Unit 3 and our focus will be entirely on homogenization, the technology behind the disruption of fat globules. The contents we will cover in this unit include the basic principle and theories of homogenization, the classification of homogenizers, the different types of homogenizers, the power requirements for operating them, and the essential care and maintenance needed to keep them running smoothly. Let's start with the basic principle. Homogenization is the process of subjecting the fat globules in milk to a high-pressure treatment. This action breaks them into much smaller globules that are evenly dispersed throughout the milk. This prevents or significantly delays the formation of a cream layer in full cream milk. The mean diameter of the fat globule is reduced by a factor of about 10. To understand why this is necessary, we must look at milk fat. It exists as an oil-in-water emulsion. These spherical droplets are enclosed by the milk fat globule membrane, or MFGM. Their diameter can range from 0.2 to 15 micrometers, with the bulk ranging from 1.0 to 8 micrometers and a mean diameter of about 3.5 micrometers. Because they are lighter, they rise and form a cream layer. The need for homogenization includes counteracting this creaming effect, improving the stability of the emulsion against partial coalescence, creating desirable rheological properties like mouthfeel, and for recombining milk products like milk powder into liquid milk. The purpose of homogenization varies by product. For milk and cream, it prevents cream separation. For coffee cream, it improves flavor, increases whitening power, and increases viscosity. For yogurt, it helps form a more stable gel. For ice cream mix, it reduces fat separation during freezing. And for full cream milk powder, it minimizes the separation of free fat. The principle of how a homogenizer works involves forcing the liquid through a very narrow gap. As the liquid passes this gap, its flow velocity increases dramatically. The speed increases until the static pressure drops so low that the liquid literally starts to boil, a process known as cavitation. In the homogenization process, large fat globules enter the valve with a velocity of only 0.3 to 3.5 meters per second. They pass through a valve clearance of about 300 micrometers, where their velocity skyrockets to 100 to 250 meters per second in less than 0.2 milliseconds. This causes a massive pressure drop and cavitation. When the liquid leaves the gap, the speed decreases and the pressure increases again, causing the steam bubbles to implode. This intense energy release creates turbulence that tears the fat globules apart into smaller homogenized globules of 0.1 to 3 micrometers, also causing a slight temperature rise. The splitting of the globules happens due to intense forces. The globules become wavy and constrict before finally disintegrating into individual droplets. Three main theories explain the forces at work: cavitation, turbulence, and laminar shear. This illustration shows the location of these forces within the homogenizer valve. High laminar shear occurs as the product flows through the narrow gap. Cavitation happens as the pressure drops, and turbulence occurs as the product impacts the ring, leading to the fragmentation of the globules. Several factors affect homogenization. Temperature is critical. The process is most effective above the melting point of milk fat, which is 33 degrees Celsius, and is typically done at 60 to 70 degrees Celsius. Pressure is the other key factor. In a single-stage homogenizer, pressures range from 150 to 200 kilograms force per square centimeter. In a second stage, lower pressures of 20 to 40 kilograms force per square centimeter are used. This table provides homogenization pressure in different units. For single stage, it's 150 to 200 kilograms force per square centimeter, 10 to 25 megapascals, 2000 to 3000 psi, or 100 to 250 bars. For the double stage, it's 20 to 40 kilograms force per square centimeter, 2 to 5 megapascals, 400 to 600 psi, or 20 to 50 bars. The homogenizer itself was invented by a Frenchman, Auguste Gaulin, in 1899. Homogenizers are classified based on their stages. There is single-stage homogenization and two-stage homogenization. In single-stage homogenization, the product passes through one set of a forcer, impact ring, and seat. Two-stage homogenization adds a second, lower pressure stage. Two-stage homogenization is used for products demanding a high viscosity, as it allows some cluster formation, and for products with a high fat content. The first stage operates at 150 to 200 kilograms per square centimeter, and the second at 20 to 40 kilograms per square centimeter. The best results are achieved when the pressure of the second stage is about 0.2 times the pressure of the first stage. The design of a homogenizer includes a main drive motor, a V-belt transmission, a pressure indication system, a crankcase, pistons, piston seal cartridges, a solid stainless steel pump block, and the homogenizing valve assembly. This slide shows an image of a modern homogenizer from GEA. The homogenizing valve comes in several designs. It can have a conical shape, a profile that causes changes in flow direction, a simple plate valve, a grooved valve face to create alternating stresses, or a design with a breaker ring. Valves can also be classified by their shape, such as ball, poppet, or mushroom valves. The pump is a critical component. It is typically a 3 to 5 cylinder plunger type pump capable of generating pressures up to 250 kg per square centimeter or higher. The uniformity of the pressure it delivers is directly related to the quality of homogenization. This slide shows an image of the pump assembly. Another image of the pump components. There are different pump types. A single plunger pump produces a pulsating pressure and suffers from rapid wear. A rotary pump provides a more uniform pressure. A key operational challenge is that above a certain speed, it becomes difficult to get proper valve action. The plunger cylinders may not fill entirely on each stroke, leading to air entrainment in the product. This causes pressure fluctuations, noise, and reduces homogenization efficiency. The pump is driven through a reduction gear and a V-belt drive. It must be readily disassembled for cleaning. The pump is made of stainless steel, and the piston seal rings are made of a soft composite material. An inlet strainer is installed to prevent coarse particles and other materials from entering the pump. This ensures uniform operation and prolongs the machine's life. The strainer has a removable perforated metal screen and must be large enough to prevent rapid clogging. A pressure relief valve is essential to protect the machine from overpressure. This valve will either stop the machine or bypass the milk to prevent damage. It is set to activate at a pressure slightly above the normal operating pressure. The pressure gauge indicates the operating pressure. It must be a sanitary type to prevent contamination. These gauges need to be tested periodically for accuracy. Ammeter-type pressure indicating devices are also used for their simplicity, but can be affected by friction in the drive. Now let's look at the working in detail. Milk enters the valve seat at high pressure but low velocity, around 4 to 6 meters per second. It then enters the narrow gap between the valve and the seat. Here, its velocity rapidly increases to 200 to 300 meters per second in about 0.2 milliseconds, and the pressure drops, causing cavitation. The intense energy release creates turbulence, and localized pressure differences tear the fat globules apart. The fat globules then impinge on the impact ring and exit at a pressure sufficient for movement to the next step. The entire homogenization phenomenon is completed in less than 50 microseconds. There is a tendency for the reduced fat globules to clump together. A second stage valve is used to separate these clusters into individual fat globules. For sterile products, an aseptic homogenizer is needed. This is because the homogenizer must be placed downstream of the sterilizing section in a UHT plant. An aseptic machine has special demands. It must be able to handle the pre-sterilization process, which involves heating to 120 to 140 degrees Celsius for 20 to 40 minutes to kill any microorganisms. This requires upgrading all seals and gaskets to withstand high temperatures. Furthermore, care must be taken to ensure no microorganisms can enter and recontaminate the sterile milk. This is achieved by prolonging the pistons, doubling the seals, and forming a sterilization zone between the seals by flushing with steam or hot condensate at 120 degrees Celsius. This slide shows an image of an aseptic homogenizer. An automatic damper is used for longer running times. It reduces pressure peaks and eliminates cavitation. It absorbs pressure variations and shocks. An automatic air refill maintains an air cushion inside the damper to ensure smooth operation. Without this cushion, vibration and cavitation would occur, shortening the running time. Homogenization can also be classified by how it's applied in a process. In a split system, only the second stage is placed downstream of the sterilizer, which is less expensive to operate. In a full or total homogenization system, used for UHT milk and cultured products, all the milk is homogenized after standardization. In partial homogenization, skim milk is not homogenized. Instead, cream together with a small proportion of skim milk is homogenized. The efficiency of homogenization is measured by the mean droplet diameter, specifically the volume surface diameter. It is calculated by the sum of n_i times d_i cubed, divided by the sum of n_i times d_i squared, where d_m is the mean diameter and n_i is the number of droplets in size range I. This slide shows milk, highlighting the effect of homogenization. This diagram illustrates the change. Before homogenization, we have separate casein micelles and fat globules. After homogenization, we see the formation of fat casein micelle aggregates, where the new smaller fat globules are covered with casein proteins. The advantages of homogenization are numerous. It leads to smaller fat globules and less creamline formation. The milk has a whiter, more appetizing color. It has reduced sensitivity to fat oxidation. It improves digestibility due to better fat absorption and protein utilization. It provides a more full-bodied flavor and better mouthfeel. And it ensures better stability of cultured milk products. However, there are some disadvantages. Homogenized milk is somewhat more sensitive to light, both sunlight and fluorescent tubes, which can result in a sunlight flavor. It might also be less suitable for the production of semi-hard or hard cheeses, because the coagulum becomes too soft and difficult to dewater. Now let's discuss the power requirement. The power needed to drive the homogenizer is directly proportional to the operating pressure. The basic formula is E equals P times Q, where E is power, P is operating pressure in kilogram per square meter, and Q is the volumetric flow rate in cubic meter per second. The electrical power input in kilowatts needed is given by a more detailed formula. E equals Q underscore IN times the quantity P underscore 1 minus P underscore IN divided by 36,000 times the efficiency of the pump times the efficiency of the motor. Here, Q underscore IN is the feed capacity in liters per hour, P underscore 1 is the homogenization pressure, P underscore IN is the inlet pressure to the pump, and the N values are efficiency coefficients. The homogenization process also causes a rise in temperature. Every 4 megapascals, or 40 bars of pressure drop, raises the temperature by 1 degree Celsius. The temperature rise is calculated as theta equals delta P divided by 40, where delta P is the pressure drop. Therefore, the outlet temperature equals the inlet temperature plus delta P divided by 40. This diagram provides an example of energy, temperature, and pressure in a homogenization process. Milk enters at 65 degrees Celsius and 2 bars. After the piston pump, it's at 68 degrees Celsius. After the first homogenization stage at 200 bars, the temperature rises. It then goes through a second stage at 40 bars before exiting at 70 degrees Celsius. Finally, we come to the care and maintenance of homogenizers, which is crucial for their longevity and performance. Wear is a major issue. This slide shows the wear pattern created on the forcer of the valve. The stainless steel seat also wears out over time, as shown in this image after 600 hours of operation at 600 bars. Calcium deposits from the milk can also cause significant wear on the components. The welds themselves will lose their proper shape over time and may form grooves. They need to be reground or replaced. If the wear is on up to 2/3 of the surface area, relapping the valve with a carborundum paste can rectify it. Further wear will cause deep erosion grooves, recognized by straight lines radiating outward, leading to a rapid loss of homogenization efficiency. Pressure gauges must be filled with a glycol fluid to reduce corrosion and dampen vibrations. They must be from time to ensure accuracy. The pressure gauges measuring the oil pressure in the drive must also be checked frequently. On the drive end, maintenance involves checking the eccentric shaft, connecting rod, and crosshead bearings for excessive wear. The eccentric shaft lobes should be checked for scoring and ridging. Drive shaft bearings must be checked for play. The oil sump strainer should be cleaned. The low oil pressure switch needs to be checked. The lube oil should be drained, the base cleaned, and new oil replaced. The oil filter must be changed, and all belts should be inspected. On the product end, the cylinder head must be disassembled. The pump valves and seats should be checked for erosion grooves, pitting, and cracks. The plungers and related parts need to be checked for wear and replaced if necessary. The homogenizing valve must be inspected for excessive wear. Finally, all gaskets should be replaced with new ones before reassembling the cylinder head. This final slide shows another image related to homogenizer maintenance. Thank you for joining this comprehensive class on homogenization. We covered everything from the basic principles and physics to the intricate design of the machines, their operation, and their maintenance. This process is fundamental to creating the consistent, high-quality dairy products we all enjoy. Thank you. See you in the next class.